Okay, we continue our work with contours and edges. Today I am going to discuss with you the last group of examples related to this topic. So in this example, it is number 17 here, we are going to work with IMAQ Find Edge 2 function. This function is specially used to define edges with straight line character. How to find it? Not difficult. You can go to the main palette here and go to machine vision and locate edges. I think there. No? Oh, yes, here. IMAQ Find Edge 2. IMAQ Find Edge 2. If I click and put it here, it will be the same as this one. Okay. So this function detects the straight line edges of objects. So I am going to demonstrate this for you. As you see here, we read an image and display it in the front panel, and also it is displayed on a special window externally. It is given number 0. So we have two displayed images. The function has an input here, which is the descriptor of the region of interest. So we are going to display a region of interest. Normally we do this as a rectangle. And the other input here is coordinate system. Really, we are not going to settle or to variate any parameters here, not required. Options here, some cities also, you can manipulate them. As you see, if you want the search, which is done by this function, to be from left to right or from right to left, up, down, down, up, and so on. Also, if you want to find all edges or some edges, the first edge, the last edge, and so on. Falling edge, rising up edge, and so on. Here also you can manage the kernel size as usual. And the other elements downwards here are rarely used or manipulated. So we go back to our block diagram. Here is the output, straight edges. As you see, it is an array of clusters. You can guess that every cluster includes an X and Y coordinate. And the number of clusters represents the number of points, which are at this straight edge. And that's it. So if we go and open the front panel here, I have read this function, this image. It is called, I don't know if it is a clamp PNG or not. Let me see. It cannot be a clamp PNG. I have written there in order not to forget. It is called overlay. Overlay, and the name of the file shapes PNG. So you go here over, this is overlay. You open it. Here is the shapes. You open it, and this is the shape which I'm working with. Of course, there are other shapes included, maybe downwards here. You can select any you want. So this is the selected shape. And as you see here, the selection is left to right, while the edge which is detected here is from down to up. So when I run the program, it should be from left to right. He is saying invalid region of interest. Okay, we shall make a region of interest. So now the region of interest exists, and when I run the program, as you see, this is the edge, left to right, the last one here shown. Let us try the opposite from right to left. Does it show the opposite one? Right to left. When I run it, it shows this edge detected. And the coordinates of this edge also, as you see, are shown here in pixels X and Y for each point of the edge. It begins with the point 362 X and Y 48, 362, 48, where it is here 364 here in this area, 363, 364, so it is here. And this is the X, yes, 362, and the Y is given here as 68. It should be less than 64. Anyhow, about this point. If you go down, for example, you will see the other points. For example, 361 by 105. And go down until you reach maybe the final. It should not be shown here because I have shown only a limited number of these points. If we want from up to down, so as usual, also we can do bottom to top. So when we run the program, here is at the top edge and so on. Okay, what else interesting here? I have also noted you can use the clamp PNG file. Okay, let us try it also. We go to the images and go to clamp PNG. Clamp. Maybe I missed it. Color. Calibration 15. Color. Let us again try. Clamp PNG. Paint parts. PCB. Rotate. Screw. It is not there. Anyhow, this is not that interesting, we can look at any other figure here. Let us see the pictures, for example, maybe there. Well, this is a good example because it has good configuration. If we put it there, the battery clamp, and put it here now. And let us try to find the edge in this area, the straight edge in this area. So we need to draw a region of interest. And it is given from bottom to up. So I think here it will show this part. From down to up, this is the first one it meets. So this straight edge is detected first. Did we say the number or something? Rising edges not fixed here. All edges may be more interesting. Let us try it again. No, it doesn't. It shows the first one which it meets here. This edge at first. If you need to know this edge, of course you have to maybe put the region of interest in this area like this. And now if you run the program, it will give you the straight edge and this portion here. And if you need this one, you have to raise it a little bit upper, and then it will give you the other. Oh, okay. And now it will give you this region and so on. So I think the idea is clear. I think nothing is left without explanation. If we go back to the block diagram, the last look here, nothing. What I also wanted to say, I didn't show you the externally displayed image. Here it is. It is displayed here, and you can work with it. You can also, for example, here. No, it doesn't catch up the region of interest because this region of interest was built by creating the property node of this image here, not this one here. This is the only reason. So you cannot work with it there. It only just shows the edges which you detect. Okay. So we leave it and go to another example. Don't save. Example number 18. I think now you are accustomed and you are familiar much better than before regarding the basic components of any of these virtual instruments. And you can guess and read it easier than before. So as you see from left to right, we have here a file and we have read this file and displayed the image here. And now we will work with this image. Okay, then what do we have? We have here a cluster which contains the coordinates of a line. You remember the line is characterized by 2 points, the first point at the beginning and the end point. And they must be given, of course, values. Here they are given values 0. Not used. In other words, not used. But this cluster now is the input to this converter, which converts the line to a region of interest. So the region of interest here is a line. And it gives an output, the descriptor of the region of interest. This is the cluster which represents the descriptor. and it is input to the loop. Here it is read. You can convert it is write. You can convert it to read. Here it is converted to read. If I click here and it becomes another one. So I do not need to do that. So this image node, and this is the same image node. Here it only reads, here it writes. It is converted to write. And now, as usual, we have two structures, the while loop and the case loop or state case loop. Here we see, you remember, when we wanted to enable the selector terminal of the case structure here, we enabled it differently, sometimes by doing a click, and sometimes when we draw a rectangle, for example, or a line on the image. So the drawing itself is the triggering action which makes this terminal high and which makes this structure to implement all the code inside it. If the image exists as it is here and in the front panel, you remember, and not externally displayed, so we use the invoke method, which includes get last event. And the last event here is the draw event. If you click here, you see draw event, click event, size event, if you want to change the size, and so on. We are interested with the drawing of the rectangle as a region of interest over the line. So the draw event, which initiates the functioning or the work of this case. Here is an OR function, which gives high or true output when any of the inputs here is true. The first one of them, when the iteration is not equal to 0, it begins with 0. But when it is 1 or 2 or 3 also, it gives high. And the program runs without having this. But if you want the program to run when you draw, so this will be high at the output because the type of the event is not equal to 0. It is equal to value. And here we will have a high. So this combination is just to initiate the working of the internal case structure. And the case structure, as you remember in your last lecture, we have said that we can use IMAQ Edge tool 3 in order to define the number of edges which faces the rectangle or the line which crosses it. And here this is IMAQ region of interest profile. It is used normally to draw the profile and see by eyes the edges and how they arise and fall. Practically, this is what we want. And the input here of this function, normally we have two inputs. One of them is the image itself, which we have displayed. And the other one is as you see, the cluster, which represents the descriptor of the region of interest. Indeed, this input, the image and the descriptor, also are inputs for the IMAQ region of interest profile function. Here is the image input also, it is there and here, and this is the descriptor also, it is here and it is also there. So, systematic work. Concerning the input here, which is the process, you remember, it is just a way to select some options. As you remember, when you go to the block diagram, here the process, you can get all edges or get the first and last edge, get the first edge only or the best edge. So it depends. Let us say get first and last, and then we will check with this. Let it be first and last edge. And now we go back and see what do we have. At the output here, as you see, here is the information, which the edge information. And this is, as you see, an array. And here I find the size of the array, label it. It is better to see what it is. Array size. And this is the size of the array, which gives you the number of edges which is going there. Number of edges is the size of the array itself. Here, what I have done is some additional work to show you. I have indexed first this array. The array could be indexed differently. It could be indexed by using a for loop. And now it is indexed at, and now we have a lower level array, or it could be indexed by using index array function. The index array function is here, as you see, index array. And the output now, as you see, by using the, by using the unbundle by name. Why did I did that? I have to show you the name only. The unbundle by name label, unbundle by name here, and also here unbundle by name. And I extracted the location of the elements of the edge. And then I managed also here to match between the output cluster, which is here, and the input cluster for IMAQ overlay rectangle function. I am doing that to show you that we can get the result here exactly the same as we do it here. And I am telling you also faithfully that we can work without these things. The information which we need are existing here, and that's it, because the most interesting information for us now is the number of edges which faces the region of interest here in our case. Okay, so with this description, we go back now and try, this is our image. It is called battery clamp, battery image 00 JPG. And here we have written get first and last edge. If I run the program, now let me draw a line through it. Now the line, this is in green, as you see, it comes to this point, and now it crosses the edge. This is the first edge between white and black. This is the first edge. And then we have asked to show us the last edge. And this is the last edge here, as you see, when the line exits the black region here to the white region. So as you see, we are from high to low, the first one from high to low, and the last one also, no, from low to high, from low to high. And here we can guess the number of edges which we have. 1, and this is 1, 2. This is which are you are interested with. Let us see if we show all edges. I will get first edge, for example. Okay, run it. I now cross it. Sorry, I didn't cross it. Why it is running? Okay, let us go, stop it here, and go to the front panel, and draw a line. We have said we wanted to get the first edge. If we run it, this is the region of interest. Run it. It is 0. It is showing 0. Why it is showing 0? Again, it is running. It is running. Okay. Get the first edge. This is the first edge. It is yes, exactly. So it is showing the first edge. It takes some delay to show it. So it has shown this point here, which is the first edge, which we have here. So it is normal. And the number of edges detected is 1. So it's okay. No problem. Okay, let us try to find all edges. I have to stop it. Get all edges. And now let me run it. What do we have? This is one edge. This is the second edge. This is the third edge. Here in this area, it seems to me that there is a valley, 4th and 5th, and 6th and 7th. So a number of edges detected are 7. But here it is not clear for you because the area here is grayscaled and not the contrast is not sufficient to guess. That's it. Okay. So I think let us go back and see if we can investigate another things. No, I think everything is discussed okay, normal. We did not miss anything here. Okay, so we go and try to understand or to discuss with another example. Example number 19. Okay. The type of the file is TIFF. The name is holes. It is imported from LabVIEW folder. Here we are using IMAQ detect circles. Really, this is not a function which detects only circles. It detects only other regular shapes like ellipses, like lines, and like rectangles. But I have selected the circles. You can work with any of them. So this is a function. And this means that this algorithm inside this function can classify the shapes there and can detect the required shape and the number of them also. The configuration for that is not difficult. All what you have this file, and to read the image, and this now the image. The image is colored. So it is converted to a grayscale and input to this algorithm. At the output here, you get the number of matches returned and how many circles are there. And also, here is for information, it is called the circles output. It is an array of clusters, as you see. It contains the coordinates of each circle. And this is the array we are talking about. So let me show it to you. Here is the first circle, the second circle, the third, and so on, which are detected. And every circle is represented by its x, y coordinates and its radius. So it calculates for you the coordinates x and y and the radius and gives you a score which shows to which degree the algorithm is confident when judging that this is a circle. Here is 987 from 1000, 98 or 99 approximately percent, he is sure. For this circle, for example, he is sure 98.3%. All of them here is 97.1%. But all the time he calculates the coordinates and gives you the values of them and the radius for the detected circuits. Here you can see that I have managed to give you the answer differently. So here you have also the same answer. This is the coordinates of the first circle and its radius and the score, and the same thing repeats for other circles. Number of matches is given here 7. If we go and look at the figure which we have here, really we have 1, 2, 3, 4 circles, but this is a rectangle, and this is a rectangle, and this is a rectangle. The total of all is 7, indeed, and he said that the number of matches is 7. So you can conclude that he considers this square as a circle. This is some kind of rounding because this rectangle is very small area, and because of that, the algorithm just judges that this is a circle, and it seems to me that the confidence degree for these three, which is the lowest here, let us see, 87. you can see, first it was 97%, now 87.6%, 87.7%, and 87.7%. This is because he is not completely confident as with the other cases, which were true circles. You have to note that. Okay, so what I did here also, I have taken this array, converted the array to a cluster, then I unbundled the cluster. I took the first circle and I found its x and its y and its radius. And these values, when I run the program, has to be shown for us. Here they are, x, y, and the radius. X 300, this is the first circle, which is 330. Here 92, approximately it is rounded to 92. The same 207.13, here 207.1 rounded. Here radius 5, 3, and so on. So I intentionally wanted to show you how you can find all the other values of all other circuits also, if you need. But of course, this is just to show you the technique, not more. Here, this cluster contains all this information directly, and you can see it as shown in the front panel. Well, I think this is also a good thing to know about. And now let us move forward and also discuss with you another interesting examples. 20. Okay. Let us see the block diagram to have an idea about what is there, and then we will discuss how it work and how to do something. So what do we have here? We have a file read by the read function, and the output is displayed as an image here. Good. The image now here is taken, and we have extracted its resolutions, the X resolution and the Y resolution. I mean by that the values of the pixels of the image at the X coordinate and at the Y coordinate. This is interesting for us because we need exactly to enclose all the image and consider all the image as a region of interest. So here, the lower point, which is X and Y of the image, and the upper point is 0 and 0. When you consider, for example, this image here, this point, the upper left is given coordinates 0 and 0, and this point, which is down here, the rightmost and down is the other point which describes the image. The distance from here to here is the X resolution, and this distance is the Y resolution. So we took both of them in order for the region of interest to enclose all the image. And now this cluster is output here with these values 0, 0, and the X resolution and the Y resolution, which will be displayed when we run the program. The image is not going to rotate, so the angle here of rotation is equal to 0. I put it 0. And now this cluster is converted to an array, and this array again is converted to a cluster, but this cluster now is has I have changed the size of this cluster by right-clicking on it here, and you look at the size 4. Normally, when you apply such a function, array to cluster, it has the maximum possible size, which is 9. 9 does not match with the 4 elements in the cluster here of this converter, which converts the region of interest, which converts the rectangle here. This is a rectangle, which converts it to a region of interest. So I have managed to make them compatible to each other, the cluster here with the input cluster, which is here. And now this works, and this is the descriptor, which feeds, the contour, extract contour function, and it feeds the converter, which converts rectangle to region of interest. Okay, what do we have then? This is the most important now. We are talking about contours. This means that we are going to extract contours. As a system here, we have mentioned, okay, let us do search by using the rectifier from left to right. Of course, you remember I told you you can open it and select depending on whether you have a rectangle as a region of interest or you have an anomalous. We have a rectangle, so I take the rectangle and take it from left to right. It could be from right to left. Sometimes it makes no difference, and sometimes depending on the shape and what you want, it makes some difference. So it is selected as you see. And the input also is the descriptor and the image. This is the destination of the image, destination contour image, and this is the image, the main image which we work with. Here, this is for settings, not more, curve extraction settings. Here they are. You decide, for example, what is the thresholding edge. Are you going to carry out contour tracing, or you are going to work just as a filter and so on? I want as a tracing. And you have to select some of these values also which affect the nature of the image. Okay, so let us go back and continue our talk. So what do we have there? So at the input of the IMAQ extract contour, we know now everything, and all these things are familiar to us here. What do we have as the output? We used yesterday this function, IMAQ get contour information. Here we have an array which contains the coordinates of all the points which constitute the contour. Or you can have it here directly without including this function. You can have it here by using contour points. And this is also an array. And this array, if you open it here, it gives you the values of x and y for each point of the contour. Okay. Now, I wanted to display the contour of the image. This is one important thing. And this is really sometimes required, and to be confident and to be sure that you are doing well. Indeed, the target of the function IMAQ extract contour, it gives you the array with the coordinates. But as you see here, I have managed to use XY graph to display the contour itself. Here it is displayed really. Here is the image itself. It is, as you see, a spider with these legs and head and the body. What I have received, it was okay. I received the contour of each of the legs and the body, the external contour of all the body, and it's perfect without any problems. But the bad thing here is I found it upsetted. The head of the spider is down, and it is upsetted. It is not normal. Really, I tried to rotate it, to make it normal with the head upwards. I could do it, I could rotate it for 90 degrees, but it took much time. And I suppose it will take much time to rotate it for another 90 degrees. So what I did the following here. As you see, I have gone like this. I took the image, the original image, and I wanted to overlay this array of points on the image. If you overlay this array on the image, really you cannot distinguish between both. They are exactly on each other. The calculations here is very fine and very accurate. So how to show it to you? Well, I took this function, it is IMAQ multiply. IMAQ multiply function, and I multiplied the image with an empty source. Okay, I got at the out, and here I gave a constant equal to 0. So I got at the output a square image which is black. Now I reversed this image black. At the output here, I have got a white rectangle. Now I overlay the edge, the contour here, the overlay, the contour, this function, IMAQ overlay points. I overlay these points on this image, which is white, and I have got this picture here. This is now the spider is vertical, and it is clearly seen as this is the original one. This is the spider drawn by using the contour itself and vertically, not upsetted as it was before. What else? Here the color, you can manage the color. I have made it like this to distinguish it from others. To be sure that it is the same, let me first put it maybe. Okay, and now if you run, it will have another color as you see. Oh, keep it, no problem with it. Okay, so what else? I think all the elements are clear. How to find this multiply function? There is a very interesting set of mathematical or logic functions usually exist when working with IMAQ. It is called operators. If you open these operators, you will find here, these are not the same as the mathematical or logic operations done by LabVIEW. Here IMAQ add, IMAQ subtract. I have used IMAQ multiply function here and continued my work. Okay. So with this also we have finished this program, and maybe you feel that I am talking now more quickly because I assume that you understand better than at the beginning, because you know the expressions and you know many of the functions and the way of thinking and how we do it. Okay, so don't save. And we go to the other example. Example 21. Let me make it smaller. Okay. Here is our virtual instrument. It consists of two parts. The upper part now well known to you. We have done it just now. We have created, as you see, a descriptor here, and this is the extract contour, and we extracted the contour of the given image. This image. This image is, as you see in the block diagram, is the clamp of the battery of the car. This is our image, the general, which we have. And now when we extracted the contour really, and I displayed the contour, here is the external contour, as you see, which we found by IMAQ extract contour virtual instrument. This is the function which we get here at the output here, contour points. And this is the XY contour graph which I showed you. So up to now, nothing new. This which we have seen in the previous example. What is interesting here? It is required to find the area inside the contour, or this area. In IMAQ and LabVIEW, in many places at night site, you can see there a specific program, which is this one enclosed in the for loop. You can find the area of any configuration if you know the array of X values and the array of the Y values. Knowing these two arrays, with this code inside this for loop, you can define the area inside the configuration. The area which is defined by this contour XY. So what I did, I wanted to find the area as I showed you. I took this contour, which was extracted, and now it is indexed here. I have indexed it with the for loop. And again, I unbundled it to X and Y. And I got at the output an X array, or an array of X values, one-dimensional array here, and one-dimensional array here. And now this dimensional array, of course, I showed it here. It is shown in the, this is the X array, and this is the Y array. They are shown for you. And I have, this is the X array shown, and this is the Y array shown. But I took this array and fed it to this code and the Y array to this code in order to calculate the area. Moreover, I took the X array and Y array values to a specific function in LabVIEW called XY graph or express XY graph. How it is, where it lies, how it works. If you go to any front panel like this and you right-click here, you come to graphs here. One of them is Express. This is shortened from Express. Express XY graph. If you take it and put it here, Now you can see the block diagram, its terminal. This is its terminal at the block diagram. This is the terminal which I have worked with. So this is not necessary for me. I have fed the X to the X input and the Y to the Y input, and the output now exists automatically, the graph. And in this graph, I have again the drawing or the picture of the contour, or the picture which is made by the values of the contour which was calculated by the program. I think this is so. Let me also remind you, when you talk about the area, here is the clamp, for example. Maybe you say, we know the pixels by the abscisse and the ordinate 640 by 100 by 480. No, this is the area of the whole picture here. We need to find this black area, which is within the contour. So this area which is required, this area was found to be here 54,018 pixels only. The whole area here is much higher, maybe 2 times more than this one. Okay? Okay, so good luck to you. I think today's lectures also were very interesting for you. I think let us stop working with the edges and the contours, and I shall try to cover with you other interesting topics in the coming lectures. Hoping you the best. Have a nice day and goodbye.